All right, on the piece of paper I just gave you, because they've got the graphs, it saves you time from writing. Matter of fact, even the first thing here is already written on your paper. You're taking these notes on the paper, not in your actual notebook. And they're going to go in your notes where I told you to write that D. Okay? All right. Turns out that you can it's actually helpful to figure out what kind of a reaction to have, and actually helpful to get information from it, like the slope. If you graph the data, you're going to find you'll be graphing the data in a lab very soon. Matter of fact, we're going to do that lab on, what's today, Tuesday? We'll probably do that lab on Thursday. And it's going to take us 2 days. We have to graph it, get the slope from it, all right? And it's useful to do this. But turns out that only one plot, if you have different orders of reactions, only one of the plots is actually going to be the characteristic plot, the one that actually predicts the slope and is useful to you. And I'm going to have to talk to you about how you can determine the order of a reaction today, basically by just looking at the graph of the concentration of the reactants versus time. We can do different things to the concentration of the reactants. Sometimes we'll take the natural log of it. Sometimes we'll take the reciprocal of it. Sometimes we'll take just the concentration itself. And as you'll see with the graphs below, I know there's a lot of them, I'll eventually show you how to interpret them. So let's take a look. First off, if we have a zero-order reaction, okay, let me remind you of what that means. And first of all, it should be an oxymoron. It shouldn't be crazy to have a zero-order reactant. We saw that with my little demo up here. I could have Josh, who wasn't involved in the slow step, or I could have Olivia, who wasn't involved in the slow step, and Emily was a slow step. So, Josh could be a zero-order reactant, but there's got to be somebody controlling the rate of the reaction. That's what you would think. So I'm going to say, for a zero-order reaction, it appears like it shouldn't even be able to happen. But neither reactant has any apparent effect on the rate of the reaction. That seems to be strange. How can neither guy control the rate of the reaction? I'm saying that increasing or decreasing the concentration of anyone in this reaction has no effect. How can that possibly be? Well, you're right. That isn't normal, okay? It does happen, though. And it happens, in particular, when you have a heterogeneous, usually a solid catalyst, used in a reaction. Let me show you why. I'm going to get out of this here for a second and show you. Go back to something we saw a while ago. Remember when we covered heterogeneous catalysts? They look like this, okay? Platinum, piece of platinum. You may remember this particularly for your catalytic converter. Remember having to read that section on the catalytic converter? Adsorption, reaction, all that stuff, okay? Activation, reaction, desorption. Okay. Well, the crazy part about this is, in a reaction like this, where if you have a limited catalyst surface area, and you have pretty much an unlimited amount of reactants, neither the concentration of the H2 nor the acetylene, not acetylene, but the ethene, would really have an effect on the reaction rate. What would determine the rate? Saturation of this spot right here, this surface area. And so, as long as this is saturated, increasing the concentration of either of these two guys won't really have an effect. That's a zero-order reaction. Now, I'm just going back to show you that how you could actually have it, because it doesn't seem intuitively like you could even have such a thing, but you can. A zero-order reaction happens when a solid catalyst is used in a reaction, and the determining factor is not the concentration of the guys, the reactants that are coming together, but rather how much surface area you have of that reaction, of that catalyst. I don't know. I suppose there's other ways you could have a zero-order reaction, but that's the one I'm most familiar with, and I think that's one of the most common ways you can have one. Now, like I said, I never used to teach this before, graphically. I felt it was enough for you to understand, and I think you do by now understand what orders of reaction mean and how mechanisms work. But I have absolutely seen, and everywhere I've looked online for the AP exam, and in the books I have, everywhere I've looked, there have been questions that involve these graphs. So you're going to have to be able to use these graphs to predict whether or not something's going to be first order, zero order, or second order. So let's see if we can't figure out why they look the way they do. Okay? First off, we'll start with this zero order one. If I graph a zero-order reaction, I don't want you have all of them written down already on your paper. Don't even look at these other two right now, because you're saying, why are we even drawing those? You're right. If it was just this guy right here, that's all you really need for this one. Let me show you why. If I graphed concentration versus time, and watch what happens. As the concentration gets lower and lower and lower, does the rate change at all? Is the slope changing? No. And that makes complete sense. It has zero effect. The concentration has no effect on the rate of the reaction itself. A zero up here, to the zero order, would make complete sense for this. All right? We really don't have to look at these other two guys. That guy alone is the characteristic graph. In every case you see it, the characteristic graph will be the one that's a straight line. You say, well, but it won't be a straight line if I've got a first-order reaction. You're absolutely right. Watch. In a first-order reaction, you already know this, and I've actually drawn this graph before without telling you at the time. In a first-order reaction, one reactant controls the overall rate of the reaction. You may remember me drawing this. I used this in the beginning of this chapter, and actually, you may remember it even from Chem 1 when we talked about half-lives. Don't draw this, but let me just show you. What normally happens in a first-order reaction, all right, say I start with, 20 as my initial, in a nuclear decay, half-life, all right? It's happening at a certain rate, okay? And after the first half-life, half of that stuff's gone. Now it's down to 10. But the thing is, from 10 down to here to the next one, it's not going to be reacting at the same rate. It's going to be reacting at half that rate. It's going to be slowing down. Remember this graph, how it starts looking like that? We saw this before in this chapter. And the same thing. So half of that slows down to half. Half of that slows down to half. Okay? So the rate is constantly changing. The slope is constantly changing along that because the concentration has an effect. And that's why you get a graph that looks like this. All right? That if you graph just the concentration versus time, you'll get that kind of a graph. However, think about it. I told you you're always looking for the straight line graph. Right? Why is that? That's one of the characteristics. Taking the natural log of concentration of A versus time, and I don't know if you all know a lot about natural logs. I'm not a big fan either. You probably don't know a whole lot. But natural log is just the power to which E is raised, right? As opposed to a log, which is the power to which 10 is raised, right? Okay. Well, either way, it's powers. And that's why when I take the power out of this, when I bring him down from the x, it would be a straight line, wouldn't it? If I'm looking at just the exponents, right, it would be a straight line. Does that make sense? If I'm not looking at the concentration. So this is the graph. That's the characteristic plot for a first-order reaction. All right? And in this case, oh, by the way, in the previous case, too, K, remember K, our rate constant? He's negative slope. Why is he a negative slope in these cases? Because I was graphing the reactants, and reactants decrease over time. Whether it's a straight line or not, they decrease over time. Okay? So a negative of this slope will give me the rate of the reaction. Okay, it's going to also give me will give me the slope. Okay, all right. Now the one that's probably the most difficult to understand is probably the second order reaction. I actually brought in Mr. Gunther to try to explain it to me, but even he was saying, if you're in AB calculus, you will never have seen this before, and if you're AB and BC, it's still going to be stuff that be kind of tough. I haven't even gotten to yet because you have to take the derivative of the rate law expression of the equation, and it gets really hairy. We went through it together, and suffice it to say that I can't explain, especially since half of you haven't even had calculus. It'd be very difficult to explain why this is the case. But you have to trust me that in a second-order reaction, where you've got a concentration raised to the second power, if you graph A versus time, you get a graph that kind of looks like the one before it. It looks like concentration of A versus time for the previous one. All right? Only it's not. It actually is much steeper here and much less steep there because it's a second-order reaction. If you take the log of it, the natural log of it, you still get a curved graph. Okay? Because you won't remember it's a squared function, not a single power. All right? That's to the first order. Only if you take 1 over A and graph that will you get a straight line. Okay, graphing 1 over the concentration gives me a straight line versus time. And that's how you'll know, if you do that, that's how you'll be able to tell that you've got a second-order reaction. Now, this is the kind of questions you'll get, multiple-choice kind of questions. Well, they'll say, I've seen them, multiple ones I've been answering now, and I've got some I'm trying to make up for you for the test. It's going to ask you which of these, well, I'll give all three at once. They're also at the back of your paper. Turn that paper over, you'll see all three of these linked together. What you're really looking for, people, is where does this occur? Where do you get your, don't put up your star here, but where do you get your straight line? You can circle, you can pick a little star there or whatever. Where do you get your actual straight line graph? Where do you get your characteristic plot? There's more than one reason to do this. Yes, there's one reason to do it would be just to tell whether the reaction, I give you a set of data, you can tell whether the reaction is first order, zero order, or second order by graphing the concentration versus time, or ln versus time, or 1 over A versus time. And that would tell you whether it's first, second, or third order. Once you have that, you're able to tell K from the slope of that line, which is great. That's very useful too. So again, you can get that information from the graph. If you're ever wondering, why are we bothering to do these graphs? They actually have a purpose if you wanted to do that. All right? But this is the key. Where is the straight line? By the way, one other thing you'll notice about this plot, when you do 1 over A, notice the slope is now positive again. Does that make sense? Sure. Right? You understand why? If I'm doing concentration versus time, you're always decreasing over time. If I'm doing 1 over concentration versus time, it's got to be increasing during time because or throughout time. Okay? All right, so there you have it. I know that's kind of difficult. I told you it would be. And I have a little summary chart also on that page, besides these three all listed together. And I'll try to explain to you and go over the next couple of days the way I might ask these kind of questions. But this summary chart is more for you to look at right before we get to the AP exam sometime in the spring. Okay? It has, I made this up here. I'm going to talk about the three possibilities. Some of this you already know. Some of it you're going to see when I get to the next day's notes tomorrow. If I have a zero-order reaction, we already know. The reactants are not, no reactants are involved in the RDS, rate determining step. Okay, the slow step. You know that. You've been playing with that for the last couple of days. You wouldn't have known probably yet, but now you know the rate is going to equal K. And the units, you're going to be, when we start to calculate the rate law expression, you're going to see that the units are going to come out the way they come out in a little bit. Negative slope, not slope, because it is reactants versus time. And the characteristic plot will be concentration versus time. Compare that, I'll put all of them up at the same time so you can see. Compare that to the characteristic plot for a first order, which is a natural log of the concentration versus time, versus the second order, which is 1 over the reciprocal, that is, of the concentration versus time. And, of course, the slope becomes positive. In this one, it's negative in those. These unit parts, don't worry about that. You're going to see why those units look like they do. I can explain them a little bit right now, but trust me, they will make sense when we start calculating these starting tomorrow. But again, some of the stuff you already know. Isn't that, if you saw that, wouldn't you have said that's first order? Wouldn't you have said that was second order? You know that. You know what second order means? 2 guys involved in slow step, or involved, same guy involved twice. 1 guy involved. So you know some of this already. All right, it's just a little summary, and you're going to learn the rest of this. Kind of, you're going to be calculating this. You're going to find the units. I remember I told you how K's units are ugly. All right, look at the units. They're not always the same, depending on the kind of reaction you have. For 0 first or second order, you might have molar per second, per seconds, or per molar second. You know, I mean, it's ugly, but they're there. K is there. Remember, to make everything else work out. That's the whole point of K. All right. So the kind of questions you might get with this, if you're confused, if you're a little, you should be a lot confused, honestly. It's okay. Let's go back to real quickly. Back to this graph. The main thing to get out of this, the main thing I've been seeing when the questions I've been asked, is can you tell, and even if it's a matter of memorization for people who are not calculus people, can you tell where the characteristic plot lies? Is it the natural log of A versus time, or 1 over A versus time? That's the key, all right? And if you can figure that, if you memorize that even, if you have to, if you can't, I mean, I try to explain it as best I can, and I will as we go on. You may have to just, in the end, just know that those are the 3 places you're going to find those characteristic plots, when it's a straight line. All right, let me pause this now, and you can get back to your homework.